Hello, my name's Kurt Zarba. I'm here with Ryan Crisanti and Drew Fakari, and today we're going to discuss our findings with the optimization of an underwater glider. Our project is sponsored by LBI Incorporated. Our primary sponsor contact is Jim Rosenberger. Our faculty advisor is Dr. Fan. LBI Incorporated is a marine engineering firm that's located in Groton, Connecticut. And our primary focus is the design, development, and manufacturing of autonomous marine vehicles. They work on many government contracts and give you an idea of what kind of autonomous vehicles they deal with. On the right-hand side are some of their current designs for low-surface visibility craft and underwater vehicles. Our project focuses primarily in the current design of an underwater glider. The glider utilizes a variable buoyancy system, also through the water. It has two bladders that are located in the fuselage, one that's filled with oil and one that's not. By transferring the oil back and forth between the two bladders, the glider can set itself to be either negatively buoyant or positively buoyant. We look to maximize the glide ratio, which is simply the horizontal distance that it travels divided by the vertical distance that it rises or sinks in the water. We compare our results to the performance of other underwater gliders, which seems to be around 2 to 4.
So the way we approach solving the problem is we ran CFD simulations on the different components of the glider, so the body, wings, and tail fins. And then we created a model that took these results from the CFD components and combined it together in order to understand the full glider behavior. So by summing the forces that you see in the free body diagram, using simple Newton's law that you see on the left-hand side, you can find the velocity at the following time step, and you can iterate over this and get a transient view of the model. There's a couple assumptions in the background of this model. We assume quasi-steady state at each time step, superposition of the components. It's only a two-dimensional model, so we're not looking at roll or yaw, and there is interpolation going on.
We split the glider into components to run separate simulations on each of them for a range of angles of attacks for the wings and for about negative 90 to 90 degrees, for a range of velocities for about half a meter per second to approximately 2 meters per second, which is the range that the actual glider will see in the water. The CL and CD values calculated from our simulations were then input into the glider model.
So this is an example of some of the results that we get from the model. This animation shows how it moves through the water. And then these two plots on the right side here, it compares the results to the tests. So the two dashed lines are two experimental tests that LBI ran with the glider in the water. And then the solid lines show some results of the model and how they compare. They're not exact matches. Some of the parameters had to be tweaked in order to get approximations, but you can see that it does start to predict some behavior of the model.
Since the glider is generally pitched slightly below the direction of travel, we recommend that the glider is now pitched at approximately 15 degrees or less to maximize the lift over drag of the fuselage itself, and that the wings should have an angle of attack of 5 degrees relative to the direction of travel to maximize the lift over drag of the wings. In addition, increasing the size of the wings would significantly increase the lift of the whole glider, since the wings generate nearly all lift, but would not affect drag that much, since the majority of the drag comes from the fuselage itself.
So to summarize what we've discussed, we've completed our various CFD simulations on the separate glider components and have created an overall system model that will combine our CFD results to better determine what the glider behavior is in the water. There's a continuation of this project. We'd like to have a full 3D model of the glider, which we would run in ANSYS and with more computational power. We'd like to continue our development of the current system model. We'd also like to perform experimental testing to validate our CFD models and better increase our confidence in the system model. Thank you for watching, and I hope that was interesting.